What if I told you that the most powerful force in the universe is completely invisible? Not gravity. Not black holes. Not exploding stars. Something far stranger. At this very moment, an unknown force is pushing entire galaxies apart. It is stretching the fabric of space itself. It is stronger than gravity on the largest scales, and it appears to control the ultimate fate of the cosmos. Scientists call it dark energy. The shocking part is that nobody knows what it is. We can't see it. We can't touch it. We can't detect it directly. Yet it makes up nearly 70% of the entire universe. Without dark energy, the cosmos we see today would not exist. So what is this invisible force? Where did it come from? And could it eventually tear the universe itself apart? Tonight, we journey into one of the greatest mysteries in modern science, the mystery of dark energy. Before we begin our journey into one of the greatest mysteries in modern science, I have a small request. Many people watch these documentaries, but only a small percentage subscribe. If you enjoy exploring the universe and want to support the channel, please take a moment to subscribe. It is extremely important and helps bring more long-form space documentaries to life. Thank you very much. Now, let's begin. The universe is expanding. This fact alone is one of the most remarkable discoveries in human history. Every galaxy we observe beyond our local neighborhood is moving away from us. Space itself is stretching, carrying galaxies farther apart with every passing second. For most of the 20th century, astronomers believed they understood this process. Gravity, the force that governs stars, planets, and galaxies, should gradually slow the expansion over time. The universe had exploded into existence during the Big Bang, and gravity should be working like a giant cosmic brake. That seemed logical. It seemed inevitable. And it turned out to be wrong. Near the end of the 20th century, astronomers made a discovery so shocking that it completely changed cosmology. Instead of slowing down, the expansion of the universe was speeding up. Galaxies were not merely drifting apart. They were accelerating away from one another. Something was pushing the universe apart. Something invisible. Something powerful enough to overcome gravity across billions of light years. Scientists gave this mysterious phenomenon a simple name: dark energy. Today, dark energy represents one of the greatest unsolved mysteries in all of science. It is believed to make up nearly 70% of the entire universe. Everything we can see, stars, planets, galaxies, gas clouds, black holes, and even ourselves, accounts for less than 5% of cosmic reality. The rest is hidden. Dark matter contributes roughly 27%. Dark energy contributes about 68%. Together they dominate the cosmos, yet neither can be directly observed. Dark energy is especially mysterious because scientists do not know what it actually is. It cannot be seen. It cannot be touched. It cannot be captured in a laboratory. Yet its effects appear everywhere. Every distant galaxy carries evidence of its existence. Every measurement of cosmic expansion points toward it. Every modern model of the universe requires it. To understand why dark energy is so important, we must first understand how astronomers discovered that the universe is expanding. At the beginning of the 20th century, many scientists believed the universe was static and eternal. The Milky Way was thought to contain the entire cosmos. Galaxies beyond our own had not yet been confirmed. The idea of an expanding universe seemed absurd. Then everything changed. Astronomers began observing strange shifts in the light coming from distant galaxies. Their spectral lines appeared stretched toward longer wavelengths, a phenomenon known as redshift. The farther away a galaxy was, the greater the redshift appeared. This pattern suggested something extraordinary. Galaxies were moving away. Not because they were traveling through space like rockets. Because space itself was expanding. In 1929, Edwin Hubble demonstrated a relationship between galaxy distance and recession speed. The farther a galaxy was from Earth, the faster it appeared to move away. The universe was expanding. This discovery transformed cosmology forever. Suddenly, the universe had a history. If galaxies were moving apart today, they must have been closer together in the past. Following this idea backward eventually led to the concept of the Big Bang, the moment when the observable universe emerged from an extremely hot and dense state billions of years ago. For decades, astronomers assumed gravity would gradually slow the expansion. After all, gravity attracts matter. Stars pull on planets. Galaxies pull on stars. Galaxy clusters pull on galaxies. The entire universe contains enormous amounts of mass. Surely gravity must be resisting expansion. The only question seemed to be how much. Would expansion continue forever? Would gravity eventually stop it? Could the universe collapse back into itself in a big crunch? Throughout much of the 20th century, these possibilities dominated cosmological research. Scientists developed increasingly sophisticated models to calculate the future of the universe. Everything depended on density. If enough matter existed, gravity might eventually reverse expansion. If not, expansion would continue forever. The answer appeared within reach. Astronomers simply needed more accurate measurements. What they did not realize was that the universe had a surprise waiting for them. A discovery so unexpected that it would challenge everything scientists thought they knew about cosmic evolution. Instead of finding evidence that expansion was slowing down, astronomers would uncover signs that something invisible was accelerating the entire universe. The discovery would win the Nobel Prize. It would force physicists to rewrite cosmological models. And it would introduce humanity to one of the strangest concepts ever proposed. Dark energy. The mysterious force that appears to control the fate of the cosmos itself. For most of the 20th century, astronomers believed they understood the basic story of the universe. The Big Bang had launched cosmic expansion billions of years ago. Galaxies moved apart as space stretched. Gravity worked continuously to slow that expansion. The only uncertainty involved the future. Would gravity eventually stop the expansion? Would the universe expand forever? Or would everything collapse back together in a dramatic big crunch? Few scientists questioned the assumption that expansion must be slowing down. It seemed obvious. Gravity attracts matter. The universe contains enormous amounts of matter. Therefore, gravity should gradually reduce the expansion rate. The logic appeared flawless. For decades, cosmologists focused on measuring exactly how much the expansion had slowed since the Big Bang. Large research programs were created for this purpose. Powerful telescopes scanned distant galaxies. New techniques were developed to measure cosmic distances with unprecedented accuracy. The goal was simple. Measure the history of expansion. Determine the future of the universe. What astronomers found instead would become one of the greatest scientific surprises of the modern era. The breakthrough began in the 1990s. Two independent research teams were attempting to measure the expansion history of the universe. One was known as the Supernova Cosmology Project. The other was called the High-Z Supernova Search Team. Although they worked separately, both groups relied on the same powerful tool, exploding stars. Specifically, they studied type Ia supernovae. These supernovae are among the brightest events in the universe. For a brief period, a single exploding star can outshine an entire galaxy containing hundreds of billions of stars. Even more importantly, type Ia supernovae possess a remarkable property. They explode with nearly the same intrinsic brightness. Because astronomers know how bright these explosions truly are, they can compare that brightness with how bright the supernova appears from Earth. This allows them to calculate distances across billions of light-years. In cosmology, type Ia supernovae became known as standard candles. They serve as cosmic measuring sticks. By observing distant supernovae, scientists could determine not only how far away galaxies were but also how fast they were moving. This combination provided a way to look backward through cosmic history. Light from distant galaxies takes billions of years to reach Earth. Observing a galaxy billions of light-years away means seeing it as it existed billions of years ago. Astronomers were effectively studying ancient snapshots of the universe. The expectation seemed straightforward. Galaxies in the distant past should reveal that expansion was slowing under the influence of gravity. Instead, the observations produced something astonishing. The distant supernovae appeared dimmer than expected. At first, researchers suspected mistakes. Perhaps the measurements were wrong. Perhaps cosmic dust was interfering with the observations. Perhaps the supernovae themselves behaved differently in the distant past. The teams checked everything repeatedly. The results remained the same. The supernovae were farther away than they should have been. The only explanation that fit the data was extraordinary. The expansion of the universe was accelerating. Billions of years ago, expansion had been slower. Today, it was faster. Something was causing space itself to expand more rapidly over time. The announcement shocked the scientific community. Gravity should slow expansion. Yet observations showed the opposite. The universe behaved as if an unknown force was pushing galaxies apart. For many astronomers, the results seemed unbelievable. Entire careers had been built around models assuming decelerating expansion. Textbooks would need revision. Cosmological theories would need revision. Perhaps even our understanding of gravity would need revision. The implications were enormous. If expansion continues accelerating forever, the future of the universe changes dramatically. Galaxies become increasingly isolated. The observable universe gradually shrinks. Distant regions disappear beyond the cosmic horizon. The ultimate fate of the cosmos becomes fundamentally different from what scientists had imagined. Throughout the late 1990s and early 2000s, independent observations continued confirming the discovery. The cosmic microwave background supported the results. Large galaxy surveys supported the results. Additional supernova observations supported the results. Evidence accumulated from every direction. The conclusion became unavoidable. The universe is accelerating. Something unknown dominates cosmic expansion. Scientists needed a name. They chose a simple one: dark energy. The name did not explain the phenomenon. It merely acknowledged its existence. Dark energy became the label for whatever was driving the acceleration of the universe. More than 25 years later, that mystery remains unsolved. Astronomers can measure its effects with remarkable precision. They can calculate how much of the universe it appears to occupy. They can model how it influences cosmic evolution. Yet they still do not know what it actually is. The discovery transformed cosmology forever. It revealed that the largest component of the universe was something humanity had never anticipated. And it raised a question that continues to challenge modern physics. If dark energy is real, what exactly is causing the expansion of the universe to accelerate? Long before dark energy became one of the greatest mysteries in science, astronomers first had to discover a far more surprising truth: the universe itself is expanding. Today this idea seems familiar, but at the beginning of the 20th century it was revolutionary. Most scientists believed the universe was static and eternal. The stars appeared fixed in place, and there seemed to be no reason to think the cosmos was changing on the largest scales. Even Albert Einstein initially assumed that the universe must be stable. When his equations of general relativity suggested that space should either expand or contract, he introduced an additional mathematical term known as the cosmological constant to keep the universe static. At the time, this seemed like a reasonable solution. Then observations changed everything. In the 1920s, astronomer Edwin Hubble studied distant galaxies and discovered a remarkable pattern. Nearly every galaxy outside our local neighborhood appeared to be moving away from us. Even more surprising, the farther away a galaxy was, the faster it seemed to recede. This relationship became known as Hubble's law and provided the first clear evidence that the universe was expanding. The discovery did not mean galaxies were flying through empty space from a central explosion. Instead, space itself was stretching. A useful analogy is the surface of an inflating balloon. Imagine tiny dots drawn across the balloon's surface. As the balloon expands, every dot moves farther away from every other dot. No single dot occupies the center of expansion because the expansion occurs everywhere simultaneously. The universe behaves in a similar way, except in 3 dimensions rather than 2. Every region of space expands, causing galaxies to move farther apart over time. This realization transformed humanity's understanding of cosmic history. If the universe is expanding today, then it must have been smaller in the past. Following this logic backward leads to an extraordinary conclusion. Billions of years ago, all the matter and energy in the observable universe occupied an extremely hot, dense state. This idea eventually became known as the Big Bang theory. Contrary to popular belief, the Big Bang was not an explosion occurring inside space. It was the rapid expansion of space itself. As the universe expanded, it cooled. Particles formed. Atoms emerged. Stars and galaxies eventually appeared. Everything we see today developed from those early conditions. For much of the 20th century, astronomers focused on understanding how expansion evolved over time. Gravity seemed destined to play the central role. Since gravity attracts matter, it should gradually slow the expansion of the universe. Imagine throwing a ball upward. The ball continues rising for a time, but gravity steadily reduces its speed. Cosmologists expected the universe to behave similarly. Expansion would continue, but at a decreasing rate. The only uncertainty involved how much matter existed. If enough matter filled the universe, gravity might eventually stop expansion altogether and reverse it, leading to a future collapse known as the Big Crunch. If less matter existed, expansion would continue forever, although it would steadily slow. These possibilities dominated cosmological research for decades. Scientists measured galaxy motions, mapped large-scale structures, and attempted to determine the average density of the universe. The goal was to predict the ultimate fate of the cosmos. Everything seemed to depend on gravity. Then observations revealed something completely unexpected. Instead of slowing down, expansion was speeding up. The universe was not behaving like a ball thrown upward against gravity. It was behaving as though some unknown force was continuously adding energy to the expansion. Galaxies were moving apart faster than before. Space itself was accelerating. This discovery would eventually lead to the concept of dark energy, but before astronomers could understand the acceleration, they first needed to understand the expanding universe itself. Expansion forms the foundation of modern cosmology. Without it, the Big Bang cannot be explained. Without it, galaxy redshifts make little sense. Without it, dark energy would never have been discovered. The expanding universe revealed that the cosmos is dynamic rather than static, evolving rather than eternal. Yet it also created one of the greatest mysteries in science. If gravity should slow expansion, why is the universe accelerating instead? The answer would lead researchers toward a hidden component of reality that appears to dominate the cosmos itself. Long before the discovery of dark energy, Albert Einstein unknowingly encountered an idea that would later become one of the most important concepts in modern cosmology. In 1915, Einstein introduced his theory of general relativity, a revolutionary description of gravity that replaced Newton's understanding of the force. Instead of viewing gravity as an invisible attraction between objects, Einstein described it as the curvature of space and time itself. Massive objects such as stars and galaxies bend the fabric of space-time, and other objects move along those curved paths. The theory successfully explained planetary motion, predicted black holes, and would later become the foundation of modern cosmology. However, when Einstein applied his equations to the universe as a whole, he encountered a serious problem. The mathematics suggested that the universe could not remain static. Gravity would either cause it to contract or the structure of space-time would force it to expand. Yet at the time, nearly all scientists believed the universe was eternal and unchanging. A static universe seemed obvious. The night sky appeared the same year after year, and no evidence existed for large-scale cosmic evolution. Uncomfortable with the idea of a changing universe, Einstein modified his equations. He introduced an additional mathematical term known as the cosmological constant. This term acted as a kind of repulsive force that could counterbalance gravity. By carefully adjusting its value, Einstein created a model of a stable, static universe. For several years, this solution appeared successful. Then everything changed. In the 1920s, Edwin Hubble discovered that distant galaxies were moving away from one another. The universe was expanding. Suddenly, Einstein's static model was no longer necessary. Space itself was dynamic. According to a famous story, Einstein later referred to the cosmological constant as the greatest mistake of his life. Whether he used those exact words remains debated by historians, but the sentiment became legendary. The term he had invented solely to prevent expansion seemed unnecessary once expansion was discovered. For decades, cosmologists largely ignored the cosmological constant. The expanding universe could be described without it, and most researchers assumed gravity would gradually slow cosmic expansion over time. The cosmological constant appeared destined to become an interesting historical footnote. Then the late 20th century arrived. When astronomers discovered that the universe's expansion was accelerating, they faced a major challenge. Something was acting against gravity on cosmic scales. Something appeared to be pushing galaxies apart. Suddenly, Einstein's forgotten cosmological constant became relevant again. Remarkably, the mathematical term he had introduced decades earlier behaved in exactly the way required to produce accelerated expansion. If empty space possessed a small amount of energy, it could generate a repulsive effect throughout the universe. As space expanded, this effect would continue operating everywhere, gradually dominating cosmic evolution. Many cosmologists began wondering whether Einstein's so-called mistake had actually been one of his greatest insights. Today, the cosmological constant remains one of the leading explanations for dark energy. In this model, empty space itself contains energy. Although the amount of energy within any given region is incredibly small, the universe contains an enormous volume of space. When multiplied across billions of light-years, the total effect becomes significant enough to drive accelerated expansion. Yet this explanation introduces a new mystery. Quantum physics predicts that empty space should contain vacuum energy arising from countless microscopic fluctuations. However, theoretical calculations produce values vastly larger than those observed. The discrepancy is so enormous that it represents one of the greatest unsolved problems in theoretical physics. Somehow, the universe contains just enough energy to accelerate expansion, but far less than simple calculations predict. No one knows why. As a result, the cosmological constant occupies a strange position in science. It explains observations remarkably well, yet its true origin remains mysterious. It works mathematically, but physicists do not fully understand why nature chose its specific value. The situation is both frustrating and fascinating. Einstein introduced the cosmological constant to solve one problem, later abandoned it, and then modern observations brought it back to the center of cosmology. More than a century after general relativity was first published, scientists are still debating whether the cosmological constant truly represents dark energy or whether something even stranger is hiding within the fabric of the universe. One thing is certain, the discovery of accelerated expansion transformed a forgotten mathematical term into one of the most important ideas in modern science. And to understand whether the cosmological constant is truly the answer, we must examine the phenomenon at the heart of the mystery itself, the unexpected acceleration of space. For decades, astronomers believed they understood the overall story of cosmic expansion. Ever since the Big Bang, the universe had been growing larger. Galaxies moved apart as space itself expanded. Gravity, acting across billions of light-years, should gradually slow that expansion. The only debate concerned how much slowing had occurred and what the long-term future of the universe would be. Some models predicted eternal expansion. Others suggested that gravity might eventually halt the expansion and trigger a collapse. Virtually nobody expected the universe to be accelerating. Yet that is exactly what observations revealed. When astronomers studied distant Type Ia supernovae during the 1990s, they found that these ancient explosions appeared farther away than expected. The simplest explanation was shocking. Billions of years ago, the universe had been expanding more slowly than it is today. Instead of losing speed under the influence of gravity, cosmic expansion was gaining speed. Space itself was accelerating. The discovery challenged one of the most basic assumptions in cosmology. Gravity is attractive. It pulls matter together. Every star, planet, galaxy, and cluster of galaxies experiences its influence. Since the universe contains enormous amounts of matter, gravity should act as a giant braking system. Yet observations showed the opposite effect. Something was overpowering gravity on the largest scales. To understand how strange this is, imagine throwing a ball into the air. Normally, gravity slows the ball as it rises. Now imagine the ball suddenly accelerating upward faster and faster on its own. Such behavior would seem impossible because it violates our expectations about how gravity works. In a similar way, the accelerating universe appeared to violate cosmologists' expectations. The more scientists investigated, the stranger the situation became. Additional observations confirmed the acceleration. Measurements of the cosmic microwave background supported the result. Large-scale galaxy surveys supported the result. Independent studies using entirely different techniques reached the same conclusion. The evidence became overwhelming. The universe was accelerating. Once this fact was accepted, researchers faced an even bigger question. What exactly was causing the acceleration? One possibility was that a previously unknown form of energy filled space itself. Unlike matter, which generates attractive gravity, this mysterious energy would create a repulsive effect on cosmic scales. As the universe expanded, the influence of ordinary matter would become weaker because galaxies spread farther apart. Meanwhile, the influence of this strange energy would remain constant or even become dominant. Eventually, it would overwhelm gravity and drive accelerated expansion. This idea became the foundation of dark energy theory. The implications were profound. If dark energy truly exists, then most of the universe is not made of stars, planets, or galaxies. Instead, the dominant component of reality would be something invisible that permeates all of space. Every cubic meter of the universe would contain a tiny amount of dark energy. Individually, the effect would be almost undetectable. Collectively, across billions of light-years, it would shape the fate of the cosmos. The acceleration of space also changes how astronomers view the future. In an expanding universe without dark energy, galaxies would continue moving apart, but gravity would gradually reduce the expansion rate. In an accelerating universe, the opposite happens. Distant galaxies move away faster and faster. Over immense periods of time, many galaxies will disappear beyond the observable horizon. Future civilizations may find themselves isolated within their local group of galaxies, unable to observe the larger universe that exists today. This possibility highlights the extraordinary power of dark energy. It is not merely a curiosity affecting distant galaxies. It determines the long-term evolution of the cosmos itself. Every second, dark energy stretches space. A little more. Every year, galaxies become slightly farther apart. Every billion years, the structure of the observable universe changes because of its influence. Yet despite its enormous importance, dark energy remains mysterious. Scientists can measure its effects with remarkable precision, but they still do not know what it is. Is it truly a property of empty space? Is it a new form of energy? Could it reflect an incomplete understanding of gravity itself? These questions remain unanswered. The discovery of accelerated expansion transformed cosmology because it revealed that the universe is governed by forces humanity barely understands. The cosmos turned out to be stranger than anyone expected. What appeared to be empty space may actually contain the dominant ingredient of reality. And to understand that possibility, we must examine how astronomers discovered dark energy in the first place and why the evidence became impossible to ignore. The discovery of dark energy did not happen because astronomers were searching for a mysterious new force. In fact, they were trying to answer a completely different question. During the late 20th century, cosmologists wanted to measure how much the expansion of the universe had slowed since the Big Bang. Gravity should have been acting for billions of years, gradually reducing the expansion rate. The challenge was finding a reliable way to measure cosmic history across enormous distances. To accomplish this, astronomers turned to one of the brightest phenomena in the universe, Type Ia supernovae. These stellar explosions occur when a white dwarf star accumulates too much matter and undergoes a catastrophic thermonuclear explosion. The resulting flash can briefly outshine an entire galaxy. More importantly, Type Ia supernovae explode with nearly the same intrinsic brightness. Because scientists know how bright they truly are, these explosions can be used as standard candles. By comparing a supernova's actual brightness with its apparent brightness from Earth, astronomers can determine its distance. This technique allowed researchers to measure distances across billions of light-years with unprecedented accuracy. During the 1990s, two independent teams began using distant supernovae to investigate cosmic expansion. The Supernova Cosmology Project and the High-Z Supernova Search Team both expected to find evidence that gravity had slowed the universe over time. The farther back they looked into cosmic history, the more clearly they hoped to see the effects of gravitational deceleration. Instead, the data revealed something astonishing. Distant supernovae appeared dimmer than expected. Since dimmer objects are generally farther away, this meant the supernovae were more distant than existing models predicted. At first, researchers suspected mistakes. Perhaps cosmic dust was absorbing light. Perhaps distant supernovae behaved differently than nearby ones. Perhaps there were errors in the measurements themselves. Scientists spent years checking every possible explanation. Yet the anomaly refused to disappear. Every new observation reinforced the same conclusion. The universe had not been slowing down. It had been speeding up. The farther astronomers looked into the past, the more obvious the effect became. Billions of years ago, expansion was slower than it is today. Somewhere along cosmic history, the universe had entered a phase of acceleration. This realization sent shockwaves through cosmology. The implications were enormous. If expansion was accelerating, then some unknown influence had to be overcoming gravity on the largest scales. Ordinary matter could not explain the effect. Dark matter could not explain it either. Something entirely new was required. The discovery was so important that the leaders of the two research teams, Saul Perlmutter, Brian Schmidt, and Adam Riess, would later receive the Nobel Prize in Physics for their work. Their observations fundamentally changed humanity's understanding of the universe. What made the discovery especially convincing was the way independent evidence soon supported it. Measurements of the cosmic microwave background revealed a universe whose geometry implied the existence of a missing component. Large-scale galaxy surveys showed patterns consistent with accelerated expansion. Observations of galaxy clustering produced similar results. Multiple lines of evidence, using entirely different methods, all pointed toward the same conclusion. Dark energy was not simply a strange feature of supernova data. It appeared to be a genuine property of the cosmos. Today, astronomers continue refining those measurements with increasingly powerful telescopes and observatories. Modern surveys have observed thousands of Type Ia supernovae across vast distances. Space missions and ground-based telescopes have mapped galaxies with extraordinary precision. The basic result remains unchanged. The universe is accelerating. Dark energy appears real. Yet despite decades of progress, the fundamental mystery remains. Scientists know dark energy exists because of its effects, but they still do not know what it is. The discovery of dark energy resembles many great discoveries in science. Astronomers first noticed something unexpected. They questioned their observations. They searched for alternative explanations. Only after exhausting every possibility did they accept the remarkable conclusion. The universe contains a mysterious component that dominates cosmic expansion. And understanding that component requires answering another critical question. If dark energy is responsible for accelerating the universe, how exactly do scientists measure the expansion of the cosmos itself? The answer lies in one of the most important techniques in modern astronomy. Understanding dark energy requires understanding one of the most difficult challenges in astronomy, measuring the expansion of the universe itself. Unlike objects on Earth, galaxies are separated by distances so vast that direct measurement is impossible. Astronomers cannot stretch a ruler across millions of light-years. Instead, they must rely on clever techniques that allow them to determine how far away galaxies are and how fast they are moving. These measurements form the foundation of modern cosmology and ultimately led to the discovery of dark energy. The first step involves measuring motion. Fortunately, the universe provides a useful tool: light. Every galaxy emits light containing unique spectral fingerprints from the atoms inside its stars. When a galaxy moves away, those spectral lines shift toward longer wavelengths in a phenomenon known as redshift. The faster the galaxy recedes, the greater the redshift becomes. By measuring this shift, astronomers can determine a galaxy's recession velocity with remarkable precision. Edwin Hubble used this technique in the 1920s when he discovered that distant galaxies generally move away from us. The farther away a galaxy is, the greater its redshift and the faster it appears to recede. This relationship became known as Hubble's law and revealed that the universe is expanding. Measuring velocity, however, is only half the problem. To understand expansion, astronomers also need accurate distances. This is where things become much more difficult. Over the past century, scientists developed what is known as the cosmic distance ladder, a series of techniques used to measure increasingly larger distances across the universe. Nearby stars can be measured using parallax, the tiny shift in position that occurs as Earth moves around the Sun. More distant stars require variable stars known as Cepheids, whose brightness changes in predictable ways. Beyond that, astronomers rely on even brighter objects visible across enormous distances. Among the most important are Type Ia supernovae. These stellar explosions act as standard candles because they possess nearly identical intrinsic brightness. By comparing how bright a supernova truly is with how bright it appears from Earth, astronomers can calculate its distance. This method allows measurements across billions of light-years. Combining distance measurements with redshift measurements creates a powerful tool. Astronomers can determine not only where galaxies are located but also how expansion has changed throughout cosmic history. Since light travels at a finite speed, looking farther into space means looking farther into the past. A galaxy 1 billion light-years away appears as it existed 1 billion years ago. A galaxy 10 billion light-years away appears as it existed 10 billion years ago. In effect, telescopes function as time machines. By observing galaxies at different distances, astronomers can reconstruct the history of cosmic expansion. This approach was exactly what researchers used during the 1990s when they discovered dark energy. They expected to see evidence that expansion had been slowing due to gravity. Instead, distant supernovae revealed that expansion was accelerating. The farther back they looked, the clearer the pattern became. The universe had changed its behavior over time. Modern astronomy has greatly expanded these techniques. Massive surveys now measure millions of galaxies across huge regions of space. Space telescopes observe supernovae at extraordinary distances. The cosmic microwave background provides additional information about the early universe. Together, these observations allow scientists to measure the expansion rate with unprecedented precision. One of the most important quantities in cosmology is the Hubble constant, which describes how quickly the universe expands today. Determining its exact value remains one of the biggest challenges in astronomy. Different methods produce slightly different results, creating a discrepancy known as the Hubble tension. Some researchers believe this disagreement could hint at new physics, perhaps even related to dark energy itself. Every improvement in measurement techniques helps refine our understanding of the universe. Yet despite decades of progress, one remarkable fact remains unchanged. All evidence points toward accelerated expansion. Dark energy continues to dominate cosmic evolution. The more accurately astronomers measure the universe, the more certain they become that some mysterious force is shaping its future. Measuring expansion transformed cosmology because it allowed scientists to uncover phenomena that cannot be seen directly. Dark energy reveals itself through the motion of galaxies, the brightness of supernovae, and the evolution of cosmic structure. It is invisible, yet its fingerprints appear everywhere. And among the tools used to reveal those fingerprints, none has been more important than the extraordinary stellar explosions known as Type Ia supernovae, the cosmic distance markers that help change our understanding of the universe forever. Among all the tools astronomers use to explore the universe, few have been as important as Type Ia supernovae. These extraordinary stellar explosions played a central role in the discovery of dark energy and helped reveal that the expansion of the universe is accelerating. Without them, one of the greatest mysteries in modern cosmology might still be hidden today. To understand why these explosions are so valuable, we must first understand the challenge astronomers face when measuring cosmic distances. The universe is unimaginably vast. Galaxies are separated by millions or even billions of light-years. Direct measurement is impossible. Scientists therefore rely on objects whose true brightness is known. By comparing an object's actual brightness with how bright it appears from Earth, its distance can be calculated. Such objects are known as standard candles. Type Ia supernovae are among the best standard candles ever discovered. Their reliability comes from the way they form. A Type Ia supernova begins with a white dwarf, the dense remnant of a star that has exhausted its nuclear fuel. White dwarfs are incredibly compact. A mass comparable to the Sun may be compressed into a sphere roughly the size of Earth. In many cases, a white dwarf exists within a binary star system, orbiting a companion star. Over time, the white dwarf may steal material from its companion. As more matter accumulates, its mass gradually increases. Eventually, it approaches a critical threshold known as the Chandrasekhar limit, approximately 1.4 times the mass of the Sun. At this point, the white dwarf becomes unstable. Temperatures and pressures rise dramatically until a runaway thermonuclear reaction ignites throughout the star. The result is a catastrophic explosion that completely destroys the white dwarf. Unlike many other supernovae, Type Ia explosions occur under very similar conditions. Because the white dwarf reaches nearly the same mass before exploding, the resulting brightness is remarkably consistent. This consistency makes Type Ia supernovae incredibly useful for measuring distances. When astronomers observe one in a distant galaxy, they know approximately how bright it should be. If it appears dimmer than expected, it must be farther away. By calculating the difference between actual and observed brightness, researchers can estimate its distance with impressive accuracy. The importance of this method cannot be overstated. Before Type Ia supernovae became widely used, measuring very large cosmic distances was much more difficult. These explosions provided astronomers with reliable markers visible across billions of light-years. Some can be observed from so far away that their light began its journey when the universe was only a fraction of its current age. This ability to observe distant supernovae allows astronomers to study cosmic history directly. Looking deeper into space means looking further back in time. By comparing supernovae from different eras, scientists can reconstruct how the expansion of the universe changed over billions of years. This was precisely the approach used during the 1990s when researchers investigated whether gravity had slowed cosmic expansion. The expectation seemed straightforward. Distant supernovae should reveal a universe expanding more rapidly in the past and slowing over time due to gravity. Instead, the observations produced one of the greatest surprises in scientific history. The supernovae appeared dimmer than expected, indicating they were farther away than existing models predicted. The only explanation that fit the data was that expansion had accelerated. The universe was growing faster, not slower. Suddenly, Type Ia supernovae transformed from useful distance indicators into the key evidence for dark energy. Their observations forced cosmologists to reconsider the nature of the universe itself. The discovery was so significant that it earned the Nobel Prize in Physics and fundamentally changed our understanding of cosmic evolution. Even today, Type Ia supernovae remain among the most important tools in cosmology. Modern observatories discover thousands of supernovae every year. Space telescopes monitor distant explosions across vast regions of the universe. Large surveys use these events to refine measurements of dark energy and the expansion rate of the cosmos. Yet despite their importance, supernovae reveal only the effects of dark energy, not its true nature. They tell us that acceleration exists. They show us how expansion changes over time. But they do not explain what dark energy actually is. For that, scientists must turn to theory. They must ask one of the deepest questions in modern physics: what exactly is this mysterious component that dominates the universe? Is dark energy a new form of energy? Is it a property of empty space? Or does it point toward a deeper understanding of reality itself? The search for answers begins with the most fundamental question of all: what exactly is dark energy? More than 25 years after its discovery, dark energy remains one of the greatest mysteries in science. Astronomers can measure its effects with extraordinary precision. They can calculate how much of the universe it appears to occupy. They can observe how it influences galaxies across billions of light-years. Yet they still do not know what it actually is. In many ways, dark energy represents a strange paradox. It is believed to be the dominant component of the universe, yet its true nature remains completely unknown. Everything we see, stars, planets, galaxies, nebulae, black holes, and even ourselves, accounts for less than 5% of cosmic reality. Dark energy alone appears to make up roughly 68%. This means that most of the universe is something humanity does not understand. The mystery begins with a simple observation. The universe is accelerating. Galaxies are moving away from one another at an increasing rate. Gravity alone cannot explain this behavior. Ordinary matter creates attractive gravity, pulling objects together. Dark energy appears to do the opposite. On the largest scales, it behaves like a repulsive influence, causing space itself to expand more rapidly over time. This raises an obvious question. What exactly is producing that repulsive effect? One possibility is that dark energy is a property of empty space itself. In everyday life, empty space appears to contain nothing. Yet modern physics paints a very different picture. According to quantum theory, even a perfect vacuum is not truly empty. Tiny fluctuations constantly occur at microscopic scales. Particles appear and disappear. Energy fields permeate space. What humans perceive as emptiness may actually be a dynamic environment filled with invisible activity. Some physicists believe dark energy emerges from this vacuum energy. If empty space contains a small amount of energy everywhere, then the cumulative effect across the entire universe could become enormous. Every cubic meter of space would contribute a tiny amount. Spread across billions of light-years, that energy could dominate cosmic expansion. This idea is elegant because it naturally explains why dark energy seems to exist everywhere. Wherever there is space, there would be vacuum energy. However, a major problem arises. When physicists attempt to calculate vacuum energy using quantum theory, the predicted value is vastly larger than what astronomers observe. The discrepancy is so extreme that it has been called the worst prediction in the history of physics. Theoretical calculations exceed observations by unimaginable amounts. Somehow nature appears to suppress most of this energy, leaving only a tiny fraction visible through cosmic acceleration. No one knows why. Another possibility is that dark energy represents an entirely new field of nature. Just as the universe contains electromagnetic fields and gravitational fields, it might contain a previously unknown energy field permeating space. Some theoretical models describe this field as quintessence. Unlike the cosmological constant, which remains fixed, quintessence could change over time. Its strength might evolve as the universe expands. Such models are appealing because they offer greater flexibility, but so far observations have not provided clear evidence that dark energy changes. Yet another possibility is even more radical. Perhaps dark energy does not exist at all. Some researchers have proposed that general relativity, Einstein's theory of gravity, may be incomplete on the largest scales. If gravity behaves differently across billions of light-years, the apparent effects of dark energy might emerge naturally. In this view, the acceleration of the universe could be signaling a need for new physics rather than a new form of energy. These ideas remain highly speculative, but they demonstrate how profoundly dark energy challenges modern science. Unlike ordinary astronomical mysteries, dark energy touches the foundations of physics itself. Understanding it may require new particles, new fields, new laws of nature, or even a revision of gravity. The stakes could hardly be higher. Solving the mystery of dark energy might transform our understanding of space, time, matter, and the origin of the universe. It could reveal hidden aspects of reality that have remained invisible throughout human history. It could connect cosmology with quantum physics, helping scientists unify theories that currently seem incompatible. For now, however, dark energy remains a mystery. We know it exists because the universe behaves as though it exists. We observe its effects in the motion of galaxies and the expansion of space. Yet its true identity remains hidden. The situation is similar to standing on a distant shore and watching waves move across the ocean. You can clearly see the effects, but the force creating them remains beneath the surface. Dark energy is the invisible force beneath the cosmic waves, shaping the evolution of the universe while remaining frustratingly out of reach. And among the many ideas proposed to explain it, one stands above all others: the cosmological constant, the strange concept Einstein introduced more than a century ago. To understand why many physicists still consider it the leading explanation, we must examine the cosmological constant itself and its remarkable connection to the accelerating universe. More than a century ago, Albert Einstein introduced an idea that he would later regret. At the time, he believed the universe was static and unchanging. His newly developed theory of general relativity suggested otherwise. The equations indicated that gravity should cause the universe to either expand or contract. Uncomfortable with this prediction, Einstein added an extra term to his equations, a mathematical correction designed to keep the universe stable. He called it the cosmological constant. For many years, the concept seemed unnecessary. After Edwin Hubble discovered that the universe was expanding, Einstein reportedly abandoned the idea and considered it a mistake. Yet decades later, when astronomers discovered that cosmic expansion was accelerating, the cosmological constant returned to the center of scientific debate. Remarkably, the same mathematical term Einstein had introduced for an entirely different reason appeared capable of explaining one of the greatest mysteries in modern cosmology. The cosmological constant is often represented by the Greek letter lambda. In simple terms, it describes a tiny amount of energy built directly into the fabric of space itself. Unlike ordinary matter, which becomes less dense as the universe expands, the energy associated with the cosmological constant remains constant. Every region of empty space contains the same amount of energy regardless of how large the universe becomes. This seemingly small detail has enormous consequences. As the universe expands, matter becomes more spread out. Galaxies move farther apart, reducing the overall influence of gravity. The cosmological constant, however, does not weaken. Empty space continues containing the same energy density everywhere. Over billions of years, this energy gradually becomes more important than matter. Eventually, it dominates the evolution of the cosmos. This behavior matches observations surprisingly well. Measurements of distant supernovae, the cosmic microwave background, and large-scale galaxy surveys all suggest that the universe is currently entering a dark energy-dominated era. Billions of years ago, matter controlled cosmic evolution. Gravity shaped the formation of galaxies and clusters. Today, dark energy appears to be taking over. The acceleration of the universe is increasing because the influence of matter continues to decline while the influence of dark energy remains constant. One reason many cosmologists favor the cosmological constant is its simplicity. It requires no new particles, no exotic fields, and no modifications to gravity. By adding a single constant term to Einstein's equations, the observed acceleration emerges naturally. In science, simple explanations often prove powerful. The cosmological constant fits observations with remarkable accuracy and remains the foundation of the standard model of cosmology used today. Yet simplicity does not mean understanding. The cosmological constant introduces one of the deepest problems in theoretical physics. According to quantum mechanics, empty space should contain vacuum energy generated by microscopic fluctuations. When physicists attempt to calculate this energy, they obtain values vastly larger than those observed. The discrepancy is so enormous that it defies intuition. Theoretical predictions exceed the measured value by a factor so large that it has been described as the worst mismatch between theory and observation in the history of science. Imagine predicting the height of a mountain and discovering it should be larger than the observable universe. The error would seem absurd. Yet this comparison barely captures the scale of the disagreement. Somehow, the universe contains just enough vacuum energy to accelerate expansion, but far less than simple calculations suggest. Why this happens remains completely unknown. This mystery is known as the cosmological constant problem. Many physicists consider it one of the most important unsolved questions in science. Solving it may require a deeper understanding of quantum mechanics, gravity, or perhaps entirely new physics. Some researchers suspect that hidden symmetries cancel most of the vacuum energy. Others believe unknown mechanisms suppress it naturally. Still others argue that the answer may involve multiple universes, where only certain values of dark energy allow galaxies, stars, and life to exist. The cosmological constant therefore occupies a unique position in modern science. It is both a successful explanation and an unsolved mystery. It accurately describes observations while simultaneously raising profound questions about the nature of reality. Every measurement of cosmic expansion strengthens its status as a leading candidate for dark energy. Yet every theoretical calculation highlights how little we truly understand. Perhaps the most remarkable aspect of the cosmological constant is its connection to empty space. For centuries, humans viewed empty space as a passive backdrop against which cosmic events occurred. Modern physics suggests something far stranger. Empty space may possess energy. It may influence the motion of galaxies. It may determine the ultimate fate of the universe. The vacuum itself may be one of the most important physical entities in existence. Whether the cosmological constant is truly the answer remains uncertain. Future observations may reveal subtle deviations that point toward more complex explanations. New theories may replace it entirely. For now, however, it remains the simplest and most successful description of dark energy available to science. And if the cosmological constant originates from the energy of empty space, that leads us to an even more fascinating question. What exactly is vacuum energy, and how can seemingly empty space possess enough power to shape the evolution of the entire cosmos? When most people think of empty space, they imagine nothingness. No stars, no planets, no gas, no light, simply an endless void stretching between galaxies. For centuries, this seemed like a reasonable assumption. Empty space appeared to be exactly that, empty. Yet modern physics paints a very different picture. According to quantum theory, the vacuum is anything but empty. In fact, what we call empty space may be one of the most active and mysterious environments in the universe. Understanding this strange reality is essential because many scientists believe dark energy may originate from the vacuum itself. At the microscopic level, the universe behaves in ways that defy everyday intuition. Quantum mechanics describes reality as a sea of constantly fluctuating fields. Even when all particles are removed from a region of space, those fields remain. They never become completely still. Tiny fluctuations continue occurring everywhere. Particles can briefly appear and disappear. Energy can emerge momentarily before vanishing again. These events happen on timescales so short that they are impossible to observe directly, yet their effects can be measured experimentally. One of the most famous demonstrations of vacuum activity is the Casimir effect. When two extremely thin metal plates are placed very close together in a vacuum, they experience a tiny force pushing them toward one another. This effect arises because quantum fluctuations behave differently between the plates than outside them. The result provides direct evidence that empty space contains measurable energy. The vacuum is not truly empty. It possesses physical properties that can influence matter. This realization has profound implications for cosmology. If empty space contains energy, then that energy should contribute to the behavior of the universe. Since space fills the entire cosmos, even a tiny amount of energy per cubic meter could become enormously significant when spread across billions of light-years. This idea naturally connects vacuum energy to dark energy. Perhaps the acceleration of the universe is simply the result of energy embedded within space itself. The concept is elegant. Every region of space contains vacuum energy. As the universe expands, more space appears. More space means more vacuum energy. The cumulative effect drives accelerated expansion. At first glance, this explanation seems almost perfect. Unfortunately, a major problem emerges when physicists attempt to calculate the amount of vacuum energy predicted by quantum theory. The numbers do not match observations. In fact, they do not come close. When researchers estimate the vacuum energy expected from known quantum fields, the result is unimaginably larger than the amount required to explain dark energy. The difference is so extreme that it has become legendary among physicists. Depending on the calculation, theory predicts a vacuum energy density up to 10 to the power of 1 squared times greater than what astronomers observe. To appreciate the scale of this discrepancy, imagine predicting the weight of an airplane and obtaining a value larger than the mass of a galaxy. The error would be absurd. Yet the vacuum energy problem is vastly worse. It represents the largest known disagreement between theoretical prediction and experimental observation in all of science. This mystery lies at the heart of modern cosmology. Why is the vacuum energy so small? Why is it not zero? Why does it possess exactly the value needed to accelerate the universe? No one knows. Many physicists believe the answer could reveal entirely new laws of nature. Some theories propose that unknown mechanisms cancel most of the vacuum energy. Others suggest hidden symmetries that force the value to remain small. Certain models invoke new particles or fields that alter the behavior of the vacuum. Still others point toward the possibility of a multiverse, where different universes possess different vacuum energies and only certain values allow galaxies, stars, and observers to exist. The multiverse explanation is particularly controversial. According to some versions of inflation theory, countless universes may exist, each with different physical properties. Most might contain vacuum energies too large for structures to form. Only a small fraction would permit galaxies, planets, and life. In such a scenario, the observed value of dark energy would not require a deeper explanation. We observe it simply because we live in a universe where conditions allow our existence. Many scientists find this idea fascinating. Others find it unsatisfying. The debate continues. Meanwhile, astronomers focus on observations. Future telescopes and surveys may provide clues about whether dark energy truly behaves like vacuum energy. If the acceleration remains perfectly constant over time, the cosmological constant interpretation becomes stronger. If dark energy changes, then a more complex explanation may be required. Regardless of the outcome, vacuum energy has already transformed our understanding of reality. What once seemed like empty nothingness now appears filled with hidden activity. The vacuum influences particles, affects cosmic expansion, and may determine the fate of the universe itself. Empty space is no longer merely a backdrop for cosmic events. It has become an active participant in the story of the cosmos. And if vacuum energy is indeed responsible for dark energy, then the next question becomes unavoidable. How does this mysterious energy compete with gravity, the force that built galaxies, formed stars, and shaped the universe for billions of years? To understand the future of the cosmos, we must examine the greatest cosmic rivalry of all, dark energy versus gravity. For billions of years, gravity was the dominant force shaping the universe. It pulled matter together after the Big Bang. It transformed tiny fluctuations into galaxies. It created stars, planets, galaxy clusters, and the enormous cosmic web stretching across the observable universe. Every large-scale structure we see today exists because gravity spent billions of years gathering matter into increasingly complex forms. Yet sometime during cosmic history, another force began to take control. Dark energy emerged as gravity's greatest rival, and today it appears to dominate the fate of the cosmos. To understand this struggle, imagine a giant tug-of-war taking place across the universe. On one side is gravity, constantly pulling matter together. On the other side is dark energy, pushing space itself to expand. For much of cosmic history, gravity held the advantage. Shortly after the Big Bang, the universe was much smaller and denser than it is today. Galaxies were closer together. Matter filled space more uniformly. Under those conditions, gravity exerted tremendous influence. It slowed the expansion inherited from the Big Bang and drove the formation of large-scale structures. During this era, dark energy existed, but its effects were relatively weak. Matter dominated the cosmos. Galaxies formed. Stars ignited. Clusters assembled. The universe became increasingly structured. If gravity had remained dominant forever, the expansion of the universe would have continued slowing. Depending on the total amount of matter, expansion might eventually have stopped completely. Some cosmologists even imagined a future Big Crunch in which gravity reversed expansion and caused the universe to collapse back into a hot, dense state. But that is not what happened. As the universe expanded, something important changed. Matter became more spread out. Every billion years, galaxies moved farther apart. The density of matter gradually decreased. Gravity weakened because its influence depends on the amount of matter concentrated within a given volume of space. Dark energy behaved differently. If dark energy is a property of empty space, its density remains constant. As the universe expands, new space appears, but the amount of dark energy per unit volume does not change. This means that while matter becomes diluted over time, dark energy does not. The consequences are enormous. Billions of years ago, matter dominated the universe. Today, dark energy dominates. The balance of power has shifted. At some point in cosmic history, dark energy became stronger than gravity on the largest scales. When that happened, expansion stopped slowing down and began accelerating instead. Galaxies started moving apart faster and faster. The universe entered a new era, an era that continues today. This transition occurred roughly 5 billion years ago. By that time, galaxies and clusters had already formed. The cosmic web was largely established. Gravity had completed much of its work. Dark energy then began reshaping the future of the universe. Importantly, dark energy does not overpower gravity everywhere. Within galaxies, gravity remains dominant. The Milky Way is not being torn apart. The solar system is not expanding. Earth is not drifting away from the sun because of dark energy. Gravity remains vastly stronger than dark energy on local scales. The effects of dark energy become important only across enormous distances, where matter is spread thinly throughout space. This distinction often causes confusion. People sometimes imagine dark energy acting like a force that pushes everything apart equally. In reality, it influences the expansion of space itself. Objects already bound together by gravity remain stable. Galaxies stay intact. Planetary systems continue orbiting normally. Dark energy primarily affects the large-scale structure of the universe. Nevertheless, its long-term influence is profound. As acceleration continues, distant galaxies move farther away. Eventually, many will cross the cosmic horizon. Their light will never reach us again. Future observers may see a much emptier universe than we observe today. Over trillions of years, galaxy clusters beyond our local region could disappear entirely from view. The observable universe would gradually shrink. Dark energy would isolate galaxies from one another across vast cosmic distances. This outcome highlights the extraordinary significance of the battle between gravity and dark energy. Gravity created structure. Dark energy separates structure. Gravity builds. Dark energy expands. Together they determine the past, present, and future of the cosmos. Yet despite decades of research, scientists still do not fully understand why dark energy became dominant at this particular moment in cosmic history. The timing seems almost suspicious. For billions of years, gravity ruled. Then relatively recently, dark energy began taking over. Why now? Why not much earlier? Why not much later? This puzzle is known as the cosmic coincidence problem. Some physicists believe it hints at deeper principles governing the universe. Others think it may simply reflect chance. Either way, the transition from a gravity-dominated universe to a dark energy-dominated universe remains one of the most fascinating events in cosmic history. And because dark energy now controls the expansion of the cosmos, it influences everything from galaxy evolution to the ultimate fate of reality itself. To understand just how powerful this influence has become, we must explore how dark energy shapes the universe on the largest scales and why it may ultimately determine the destiny of every galaxy that exists. Dark energy is not merely an abstract concept used by cosmologists to explain the acceleration of the universe. It is one of the most important factors shaping the cosmos on the largest scales. Although its effects are almost impossible to notice within galaxies or planetary systems, across billions of light-years, dark energy determines how the universe evolves, how galaxies interact, and ultimately what the future of reality may look like. For billions of years after the Big Bang, gravity was the dominant force shaping cosmic structure. Matter gathered into galaxies, galaxies merged into clusters, and clusters became connected through the vast network known as the cosmic web. During this era, gravity steadily built complexity throughout the universe. However, as cosmic expansion continued, matter became increasingly diluted. The average density of matter decreased while dark energy remained constant. Eventually, dark energy began to dominate the large-scale behavior of the cosmos. Once this happened, the expansion of space started accelerating. Galaxies that were already moving apart began separating more rapidly. The farther away a galaxy is, the stronger this effect becomes. Today, distant galaxies are receding from us at tremendous speeds due to the expansion of space itself. In some cases, galaxies are effectively moving away faster than the speed of light, not because they are traveling through space that quickly, but because the space between us and them is expanding. This distinction is one of the strangest consequences of modern cosmology. Dark energy does not push galaxies through space like a conventional force. Instead, it stretches the fabric of the universe itself. As a result, cosmic distances grow larger over time, and the observable universe changes continuously. One of the most important effects of dark energy involves the cosmic horizon. Light travels at a finite speed, and because the universe has a finite age, there is a limit to how far we can see. Accelerated expansion causes distant galaxies to cross this horizon. Once they move far enough away, their light can never reach us again. They effectively disappear from the observable universe forever. This process is already occurring. Every second, regions of the universe become permanently inaccessible because expansion carries them beyond our observational reach. In the distant future, the night sky could look dramatically different from the one we see today. Galaxies outside our local gravitationally bound region may vanish from view entirely. Future civilizations, if any exist, might see only their own local group of galaxies surrounded by darkness, unaware that countless other galaxies once filled the cosmos. Dark energy therefore influences not only the motion of galaxies but also what information remains accessible in the future. It determines the size of the observable universe and shapes humanity's ability to understand cosmic history. On even larger timescales, dark energy affects the fate of structure itself. Galaxy formation gradually slows because expansion makes it increasingly difficult for gravity to gather matter into new systems. Regions of space become more isolated. The cosmic web stretches. The universe grows colder and emptier. In many ways, dark energy acts as the architect of the universe's future. Every long-term prediction about cosmic destiny depends upon its behavior. Yet despite its immense influence, dark energy remains mysterious. We observe its effects everywhere, but we still do not know its true nature. Whether it is vacuum energy, a dynamic field, a modification of gravity, or something entirely unknown remains one of the greatest unanswered questions in science. Nevertheless, one fact is clear. The modern universe is entering an age dominated by dark energy. Gravity built the cosmic structures we see today, but dark energy is determining what those structures will become tomorrow. The story of the universe is no longer simply a story of matter and gravity. It is a story of an invisible force that now controls the largest scales of existence and may ultimately decide the fate of everything in the cosmos. For most of cosmic history, galaxies have been the great builders of the universe. They formed from immense clouds of gas and dark matter, merged with one another, created countless generations of stars, and assembled the large-scale structures we observe today. The Milky Way alone contains hundreds of billions of stars, while the observable universe contains hundreds of billions, perhaps trillions, of galaxies. Yet dark energy is gradually changing the destiny of these enormous systems. Although galaxies themselves remain bound together by gravity, the space between them continues expanding at an accelerating rate. This means that while stars within a galaxy remain connected, galaxies that are not gravitationally bound slowly drift farther apart. Over billions of years, galaxy clusters become increasingly isolated from one another. The cosmic web that once connected vast regions of the universe begins to stretch and thin. Distant galaxies recede faster and faster as dark energy drives accelerated expansion. Today, astronomers can observe countless galaxies spread across the observable universe, but this situation will not last forever. As acceleration continues, more and more galaxies will cross the cosmic horizon, moving so far away that their light can never reach us again. Future observers living trillions of years from now may look into the sky and see only a handful of nearby galaxies. Evidence of the Big Bang, the cosmic microwave background, and the larger universe could disappear entirely from view. In many ways, dark energy is slowly erasing the visible record of cosmic history. The local group, which includes the Milky Way, Andromeda, and dozens of smaller galaxies, will remain gravitationally bound despite expansion. In approximately 4 to 5 billion years, the Milky Way and Andromeda are expected to collide and merge, forming a giant elliptical galaxy sometimes nicknamed Milkomeda. This new galaxy will continue orbiting within the local group, largely unaffected by dark energy on local scales. However, beyond this gravitational island, the rest of the universe will continue drifting away. Galaxy clusters that are currently visible through telescopes will gradually vanish beyond the horizon. The night sky will become darker and emptier as cosmic isolation increases. Star formation will also decline over time. Galaxies possess finite supplies of gas, the raw material needed to create new stars. As billions of years pass, these reserves become depleted. Fewer stars are born. Existing stars age and die. The bright, active era of galaxy evolution slowly comes to an end. Dark energy does not directly stop star formation, but by accelerating expansion it reduces opportunities for galaxies to interact and merge, processes that often trigger bursts of stellar birth. The long-term result is a universe containing older and older galaxies, with fewer new stars appearing. Over immense timescales, the cosmos becomes quieter. The great age of galaxy formation eventually gives way to an age of cosmic decline. Yet throughout this process, dark energy continues operating relentlessly. Every second, space expands. Every year, galaxies become more isolated. Every billion years, the observable universe shrinks as distant regions disappear forever. The fate of galaxies is therefore inseparable from the mystery of dark energy. Understanding what dark energy is will help determine not only how galaxies evolve but also what the universe itself ultimately becomes. Will acceleration continue forever? Will it remain constant? Could it grow stronger over time? The answers to these questions will shape the destiny of every galaxy in existence and determine whether the cosmos ends in eternal expansion, catastrophic destruction, or something even stranger. One of the strangest consequences of dark energy is that it changes not only the future of galaxies but also the limits of what can ever be observed. Most people imagine the universe as a vast but fixed place, where distant galaxies simply remain where they are while we build better telescopes to see farther. In reality, the observable universe is constantly changing. Because light travels at a finite speed and space itself is expanding, there are regions of the cosmos that are gradually slipping beyond our reach. Dark energy accelerates this process. As expansion becomes faster, distant galaxies move away more rapidly. Eventually, some galaxies recede so quickly that the light they emit can never reach Earth, no matter how long we wait. They pass beyond what astronomers call the cosmic horizon. This horizon is not a physical wall or edge in space. It is a limit created by the expansion of the universe and the finite speed of light. Beyond that boundary, events can occur forever without ever becoming observable from our location. The existence of this horizon means that dark energy is effectively reducing the portion of the universe accessible to observation. Today, astronomers can see galaxies whose light has traveled for billions of years across expanding space. In the distant future, many of those galaxies will disappear beyond the horizon forever. Their light will become increasingly stretched by expansion, shifting into longer and longer wavelengths until it fades completely from detectability. Future civilizations living trillions of years from now may have no evidence that those galaxies ever existed. They could look into space and see only the remnants of their own local group of galaxies surrounded by darkness. Even more remarkable, the cosmic microwave background, the ancient afterglow of the Big Bang, will eventually become undetectable as expansion stretches its radiation to enormous wavelengths. Future astronomers may be unable to observe one of the most important pieces of evidence supporting the Big Bang itself. In a sense, dark energy is gradually hiding the history of the universe. The observable cosmos becomes smaller not because galaxies vanish, but because information from those galaxies can no longer reach us. This realization has profound implications. Humanity happens to live during a special period of cosmic history when the universe is old enough for complex structures to exist yet young enough that we can still observe vast regions of space. We can study the Big Bang, map distant galaxies, and investigate cosmic evolution. Future observers may not be so fortunate. Their view of the universe could be far more limited. Dark energy therefore influences not only the future of matter and galaxies but also the future of knowledge itself. It determines what can be seen, measured, and understood. The accelerating expansion of space continuously redraws the boundaries of observation, creating a dynamic horizon that shapes humanity's ability to explore the cosmos. As scientists continue studying dark energy, one question becomes increasingly important. If most of the universe is controlled by invisible components such as dark matter and dark energy, what does that mean for our understanding of reality? The answer reveals a surprising truth: nearly everything we can see represents only a tiny fraction of what actually exists. One of the most astonishing discoveries in modern science is that almost everything humans can see represents only a tiny fraction of reality. For thousands of years, people assumed that stars, planets, galaxies, and other visible objects made up the universe. Even after the invention of powerful telescopes, astronomers continued expanding their catalogues of visible matter, believing they were gradually uncovering the contents of the cosmos. Yet during the 20th century, a surprising picture began to emerge. Observations repeatedly showed that visible matter alone could not explain how galaxies rotate, how galaxy clusters remain bound together, or how large-scale structures formed after the Big Bang. The universe appeared to contain far more mass than telescopes could detect. This invisible component became known as dark matter. Today, dark matter is believed to account for roughly 27% of the universe. It does not emit light, absorb light, or reflect light. Its presence is revealed only through gravity. Galaxies rotate too quickly without it. Clusters contain too much mass to be explained by visible stars alone. Gravitational lensing, the bending of light by massive objects, repeatedly reveals hidden concentrations of matter throughout the cosmos. Yet even dark matter is not the dominant ingredient of reality. Observations of cosmic acceleration indicate that dark energy accounts for approximately 68% of the universe. Combined together, dark matter and dark energy make up about 95% of all cosmic content. Everything familiar, stars, planets, gas clouds, black holes, humans, animals, oceans, and entire galaxies, represents less than 5% of existence. This realization completely transformed cosmology. Humanity once imagined that the visible universe represented reality itself. Now we understand that most of the cosmos is hidden. The stars filling the night sky are merely the bright surface of a much larger and largely invisible universe. Dark matter forms the gravitational scaffolding upon which galaxies are built. Dark energy controls the expansion of space and shapes the future of the cosmos. Without either component, the universe would look dramatically different from the one we observe today. Yet despite decades of research, scientists still do not know exactly what either dark matter or dark energy truly are. Dark matter may consist of undiscovered particles. Dark energy may be vacuum energy, a new field of nature, or something even more exotic. Some physicists suspect that both mysteries point toward deeper laws of physics waiting to be discovered. Others believe entirely new theories may be required. The challenge is profound because the dominant ingredients of the universe remain invisible. Astronomers must study them indirectly through their effects on galaxies, light, and cosmic expansion. In many ways, modern cosmology resembles an investigation in which the primary suspects can never be seen directly. Scientists infer their existence from clues scattered throughout the universe. Remarkably, those clues are consistent across many independent observations. Galaxy rotation curves, gravitational lensing, the cosmic microwave background, supernova measurements, and large-scale structure surveys all support the same conclusion. The universe is dominated by invisible components. This realization also changes humanity's perspective. For centuries, scientific progress often involved making the invisible visible. Telescopes revealed distant worlds. Microscopes exposed hidden biological systems. Particle accelerators uncovered subatomic particles. Yet the greatest discoveries of modern cosmology suggest that much of reality may remain fundamentally hidden. We can observe its effects, but direct observation remains elusive. The universe is therefore far stranger than it appears. Beneath the stars and galaxies lies a hidden framework of dark matter. Beyond that, an even more mysterious force called dark energy drives cosmic acceleration. Together they govern the evolution of the cosmos. Understanding them may require breakthroughs as profound as relativity or quantum mechanics. For now, however, their existence serves as a humbling reminder that humanity's knowledge remains incomplete. We have learned enough to recognize that most of reality is invisible, yet we have not learned enough to fully explain it. And among these hidden mysteries, dark energy remains the most puzzling of all because it controls the expansion of the universe itself. The next question is therefore one of the most important in cosmology: could dark energy change over time, or is it truly constant throughout the history of the cosmos? One of the biggest assumptions in modern cosmology is that dark energy remains constant throughout the history of the universe. This idea forms the foundation of the cosmological constant model, currently the simplest and most successful explanation for cosmic acceleration. According to this view, every region of space contains the same amount of dark energy, and that amount never changes. Whether the universe was billions of years younger or trillions of years older, dark energy would remain essentially the same. This model fits observations remarkably well and forms part of the standard cosmological framework used by scientists today. Yet despite its success, many physicists remain unconvinced that the story is complete. The reason is simple: we still do not know what dark energy actually is. If dark energy represents a new physical field rather than vacuum energy, its strength might evolve over time. In such models, the acceleration of the universe would not remain constant forever. Instead, it could grow stronger, weaken, or even reverse direction under certain circumstances. One of the most famous alternatives is known as quintessence. Unlike the cosmological constant, quintessence describes dark energy as a dynamic field filling the universe. Just as temperature, pressure, and magnetic fields can vary from place to place, quintessence could change as the universe evolves. Billions of years ago, it might have been weaker than it is today. In the distant future, it could become stronger or weaker still. This possibility fascinates cosmologists because it would mean the universe is even more dynamic than currently believed. If dark energy changes over time, the long-term future of the cosmos could differ dramatically from standard predictions. In some scenarios, acceleration eventually slows. In others, it becomes increasingly powerful. There are even models in which dark energy reverses, allowing gravity to regain control and alter the fate of cosmic expansion. Astronomers have spent decades searching for evidence of such changes. By observing distant supernovae, mapping galaxy distributions, and studying the cosmic microwave background, researchers can compare the behavior of the universe at different times in its history. If dark energy evolves, those observations should reveal subtle differences. So far, however, the evidence remains inconclusive. Current measurements are consistent with a constant dark energy density, but the uncertainties are still large enough that evolving models cannot be ruled out completely. Future observatories may provide the answer. Projects such as the Nancy Grace Roman Space Telescope, the Euclid mission, and next-generation galaxy surveys are specifically designed to measure cosmic expansion with unprecedented precision. These instruments will map millions of galaxies and observe distant supernovae across enormous regions of space. Their goal is simple but profound: determine whether dark energy truly remains constant or changes over time. The implications are enormous. If dark energy is constant, then Einstein's cosmological constant may be correct, and the universe could continue accelerating forever. If dark energy evolves, entirely new physics may be required. Scientists might discover previously unknown fields, particles, or interactions governing the behavior of the cosmos. Such a discovery would rank among the most important breakthroughs in modern science. It could reshape our understanding of gravity, quantum mechanics, and the origin of the universe itself. The question also connects to one of the deepest mysteries in cosmology. Why did dark energy become dominant only relatively recently in cosmic history? If it changes over time, perhaps the answer lies in its evolution. Perhaps dark energy was weaker in the distant past and only recently reached the strength necessary to dominate cosmic expansion. Such possibilities remain speculative, but they demonstrate how much remains unknown. The universe may be far more dynamic than our current models suggest. Dark energy may not be a simple constant embedded within space. It may be part of a larger story still waiting to be uncovered. For now, astronomers continue gathering data, searching for even the smallest signs of change. Every new observation helps narrow the possibilities. Every new survey brings us closer to understanding whether dark energy is truly constant or something far more complex. And if dark energy does change over time, then many of our predictions about the future of the universe may need to be reconsidered. This leads naturally to another fascinating question: what if our current understanding of dark energy is completely wrong? What if the acceleration of the universe points not to a mysterious energy, but to a deeper problem with our understanding of gravity itself? Although dark energy is currently the leading explanation for the accelerating universe, not all scientists are convinced that an invisible energy field is the correct answer. Throughout the history of science, unexpected observations have often revealed flaws in existing theories rather than entirely new forms of matter or energy. When the orbit of Mercury failed to match Newton's predictions, the solution was not a hidden planet but Einstein's theory of general relativity. When galaxies appeared to move in strange ways, astronomers proposed dark matter, but some researchers instead suggested modifications to gravity itself. In a similar way, the discovery of cosmic acceleration has led some physicists to ask a provocative question: what if dark energy does not exist at all? What if the universe is accelerating because our understanding of gravity is incomplete? General relativity has passed every experimental test with extraordinary success, from the motion of planets to the detection of gravitational waves. Yet most of those tests occur on relatively small cosmic scales. The universe, however, spans billions of light-years. Some scientists wonder whether gravity behaves differently across such immense distances. If general relativity requires modification on the largest scales, the apparent effects of dark energy might emerge naturally without requiring a mysterious new form of energy. Over the years, numerous alternative theories have been proposed. Some models suggest that gravity becomes weaker or stronger over enormous distances. Others introduce additional dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. In certain theories inspired by string theory, gravity may leak into higher dimensions, altering the expansion of the universe in subtle ways. There are also models involving extrascalar fields that modify how gravity operates across cosmic scales. These ideas remain speculative, but they demonstrate the creativity of modern theoretical physics. Another possibility is that the universe itself is more complex than standard cosmological models assume. Most cosmological calculations treat the universe as smooth and uniform when viewed on large scales. In reality, the cosmos contains enormous structures such as galaxy clusters, superclusters, filaments, and vast cosmic voids. Some researchers have suggested that averaging over these structures might create effects that resemble accelerated expansion. Although most evidence currently favors genuine dark energy, the idea continues to be explored because of the profound implications it would carry. If correct, it would mean the acceleration of the universe emerges from the geometry of cosmic structure rather than a mysterious energy component. Alternative theories are important because they challenge assumptions and force scientists to test their models rigorously. Every prediction made by dark energy theories must be compared against observations. Future telescopes will help determine whether the acceleration of the universe behaves exactly as the cosmological constant predicts or whether subtle deviations exist. If such deviations are found, they could point toward entirely new physics. This process lies at the heart of science. Competing explanations are proposed, tested, refined, and sometimes discarded. The goal is not to defend a particular theory but to discover which description best matches reality. At present, dark energy remains the simplest explanation for the available evidence. Yet history teaches that nature often surprises us. Many ideas once considered impossible later became accepted science. The true explanation for cosmic acceleration may involve concepts humanity has not yet imagined. Whether dark energy is vacuum energy, a dynamic field, modified gravity, extra dimensions, or something entirely unknown, one fact remains clear: the universe is expanding faster and faster. Understanding why may require one of the greatest scientific revolutions since Einstein. And because the nature of dark energy remains uncertain, predictions about the future of the universe also remain uncertain. Depending on what dark energy truly is, the cosmos could face several very different destinies. Some possibilities involve eternal expansion. Others are far more dramatic. Among them is one of the coldest and loneliest futures ever imagined, a scenario known as the Big Freeze. If dark energy continues behaving exactly as it does today, the most likely fate of the universe is a scenario known as the Big Freeze. Unlike dramatic cosmic endings involving explosions or collapses, the Big Freeze is a slow and relentless process that unfolds over trillions upon trillions of years. It is a future defined not by violence but by isolation, darkness, and the gradual fading of all activity in the cosmos. According to current observations, dark energy is causing the expansion of the universe to accelerate. As billions of years pass, galaxies move farther apart. The distances between galaxy clusters grow larger. More and more regions of the universe disappear beyond the cosmic horizon. Eventually, every galaxy outside our local gravitationally bound group will become unreachable. Future observers may see only the remnants of their own galactic neighborhood surrounded by an immense and empty darkness. The cosmic web that once connected vast structures across the universe will effectively dissolve from view. Yet this is only the beginning. Within galaxies, stars continue burning their nuclear fuel. Massive stars die first, exploding as supernovae and leaving behind neutron stars or black holes. Smaller stars live much longer, sometimes for trillions of years. Over time, however, even these stars exhaust their fuel. New star formation gradually declines as galaxies consume their remaining gas. Fewer stars are born. Existing stars grow older. The universe slowly becomes darker. Trillions of years in the future, most stars will have burned out. Galaxies will be populated primarily by stellar remnants such as white dwarfs, neutron stars, and black holes. Without new generations of stars, the cosmos enters what astronomers sometimes call the degenerate era. Light becomes increasingly rare. Energy sources diminish. Cosmic activity slows dramatically. As time continues, gravitational interactions gradually eject many objects from galaxies altogether. Some stars and remnants will be flung into intergalactic space. Others will fall into black holes. The remaining structures become increasingly sparse. Eventually, even black holes begin to disappear through a process known as Hawking radiation. According to quantum theory, black holes slowly lose energy and evaporate over incredibly long timescales. A supermassive black hole may survive for more than 10 to the power of 1 years, but even it is not eternal. Given enough time, every black hole will vanish. After the final black holes evaporate, the universe enters an era unlike anything we can easily imagine. There are no stars. No galaxies. No planets. No black holes. Matter itself may eventually decay, depending on the laws of particle physics. The cosmos becomes a vast, cold expanse containing only extremely low-energy particles and radiation drifting through ever-expanding space. Temperatures approach absolute zero. Useful energy becomes increasingly scarce. The universe reaches a state of maximum entropy, where no significant physical processes remain possible. This is the essence of the Big Freeze. It is not a sudden event but a gradual fading away. The universe does not end with a bang. It ends with silence. Every structure built by gravity slowly disappears. Every source of light eventually goes dark. Expansion continues forever while the cosmos becomes colder, emptier, and more diffuse. Many cosmologists consider the Big Freeze the most likely future because current observations suggest that dark energy behaves like a cosmological constant. If that remains true, acceleration will continue indefinitely. The observable universe will shrink. Cosmic isolation will increase. Entropy will rise. The long-term result is a cold and dark universe stretching endlessly into the future. Yet despite its bleak reputation, the Big Freeze also reveals something profound. The universe is dynamic. It evolves across timescales so vast that human history becomes almost invisible by comparison. Galaxies form, stars shine, black holes grow, and entire cosmic eras come and go. Dark energy appears to be guiding the cosmos toward a future unlike anything that exists today. But the Big Freeze is not the only possibility. If dark energy changes over time and becomes stronger, the universe may face a far more dramatic fate. Instead of slowly fading away, reality itself could be torn apart. This terrifying possibility is known as the Big Rip. While the Big Freeze is currently considered the most likely fate of the universe, it is not the most dramatic. Some theoretical models predict a far more terrifying future known as the Big Rip. In this scenario, dark energy does not remain constant. Instead, it grows stronger over time. As the universe expands, the influence of dark energy increases until it eventually overwhelms every force in nature. The consequences would be extraordinary. Gravity would lose its ability to hold galaxies together. Stars would be separated from their galaxies. Planets would be torn away from their stars. Eventually, even atoms themselves could be ripped apart. The entire structure of reality would unravel. The idea emerged from attempts to explore what might happen if dark energy possesses a property known as phantom energy. In standard cosmology, dark energy has a pressure that is negative enough to drive accelerated expansion. Phantom energy would be even more extreme. Its density would increase as the universe expands, creating a runaway effect. Instead of remaining constant like the cosmological constant, dark energy would become increasingly powerful with time. The acceleration of the universe would grow faster and faster. At first, the effects would be subtle. For billions of years, galaxies would continue moving apart much as they do today. Expansion would accelerate gradually. The universe would appear normal on local scales. Yet as phantom energy became stronger, cosmic structures would begin to experience its influence more directly. Several billion years before the final Big Rip, galaxy clusters would be the first victims. Gravity would no longer be strong enough to keep clusters bound together. Galaxies that had orbited one another for billions of years would drift apart forever. The cosmic web would disintegrate. Enormous structures stretching across millions of light-years would dissolve under the growing influence of dark energy. Millions of years before the end, individual galaxies would begin to fall apart. Stars orbiting galactic centers would lose their gravitational anchors. Spiral galaxies would unravel. The Milky Way itself would cease to exist as a coherent structure. Stars would scatter into expanding space. As the final moments approached, the destruction would become increasingly rapid. Perhaps only years before the Big Rip, planetary systems would destabilize. Gravity would no longer hold planets in orbit around their stars. Worlds would drift away into darkness. Moons would separate from planets. Solar systems would be torn apart. Then the process would become even more extreme. Minutes before the end, stars themselves could be destroyed. The forces holding stellar material together would fail. Nuclear furnaces that had burned for billions of years would be ripped apart by the expansion of space. Finally, in the last fractions of a second, the ultimate catastrophe would occur. Atoms would no longer remain stable. Electrons would separate from nuclei. Atomic nuclei would break apart. The fundamental structures of matter would cease to exist. Space itself would expand infinitely in a finite amount of time. The universe would end not in darkness or collapse, but in complete disintegration. Everything would be torn apart. Fortunately, current observations do not strongly support the Big Rip scenario. Most measurements suggest that dark energy behaves much more like a cosmological constant than phantom energy. The expansion of the universe is accelerating, but there is currently no convincing evidence that dark energy is growing stronger over time. Nevertheless, the possibility remains scientifically important because it demonstrates how sensitive the future of the universe is to the nature of dark energy. A tiny difference in behavior can lead to dramatically different destinies. If dark energy remains constant, the universe experiences a slow big freeze. If dark energy weakens, expansion may eventually slow. If dark energy strengthens, the cosmos could face a big rip. This uncertainty highlights how little we truly know about the dominant component of reality. Dark energy controls the future of the universe, yet scientists still cannot explain its origin. The fate of galaxies, stars, planets, and perhaps matter itself depends upon a phenomenon that remains mysterious. Few questions in science carry greater significance. The future of the cosmos hinges on understanding a force we cannot directly observe. And that is why dark energy remains one of the most important unsolved problems in modern physics. To solve it, astronomers are building new observatories, launching powerful space telescopes, and collecting more data than ever before. The next generation of instruments may finally reveal whether dark energy is constant, evolving, or something entirely unexpected. The search continues because the answer may determine not only how the universe ends, but also how the universe truly works. Among all the unanswered questions in science, few are as important, or as frustrating, as dark energy. Physicists have spent decades studying it. Astronomers have measured its effects across billions of light-years. Powerful telescopes have mapped galaxies, observed distant supernovae, and analyzed the ancient light left behind by the Big Bang. Yet despite all this effort, humanity still does not know what dark energy actually is. This is what makes it one of the greatest mysteries in modern physics. Unlike many scientific problems, dark energy is not a small detail hidden within a larger theory. It appears to dominate the entire universe. Roughly 68% of all cosmic content seems to consist of dark energy. In other words, the majority of reality is governed by something we do not understand. Imagine trying to explain Earth while knowing almost nothing about its oceans, atmosphere, or continents. That is similar to the challenge facing cosmologists today. We can observe the visible universe, but most of its contents remain mysterious. The problem becomes even deeper when dark energy is compared with the two greatest theories of modern physics, general relativity and quantum mechanics. General relativity describes gravity and the large-scale structure of the universe with extraordinary accuracy. Quantum mechanics describes the microscopic world of particles and fields. Both theories are among the most successful scientific frameworks ever created. Yet when physicists attempt to combine them to explain dark energy, they encounter major difficulties. Quantum theory predicts enormous amounts of vacuum energy. Observations show only a tiny fraction of that value. The disagreement is so large that many researchers believe it signals a fundamental gap in our understanding of nature. Some physicists suspect dark energy could be the clue needed to unify gravity and quantum mechanics into a single theory. Others believe it points toward entirely new physics waiting to be discovered. The mystery has become a crossroads where cosmology, particle physics, quantum theory, and gravity all meet. This is one reason dark energy fascinates scientists so deeply. Solving the problem could revolutionize multiple fields simultaneously. Throughout history, major scientific mysteries have often led to profound breakthroughs. The strange motion of Mercury helped inspire general relativity. The behavior of atoms led to quantum mechanics. The mystery of dark energy may eventually produce another revolution of similar magnitude. It could reveal hidden dimensions, unknown particles, new fields, or entirely new laws governing the cosmos. Some researchers even wonder whether dark energy is connected to the origin of the universe itself. The same forces responsible for today's accelerated expansion may have played a role during cosmic inflation, the brief period of rapid expansion believed to have occurred shortly after the Big Bang. If such connections exist, understanding dark energy might help explain why the universe looks the way it does today. The implications extend far beyond astronomy. Dark energy influences the fate of galaxies, the future of cosmic structure, and perhaps the ultimate destiny of reality itself. It determines whether the universe freezes, tears apart, or evolves in some completely unexpected way. In that sense, dark energy is not merely an astronomical curiosity. It is one of the central questions of existence. Why is the universe expanding the way it is? Why does empty space possess energy? Why does acceleration occur at all? These questions remain unanswered. Yet despite the mystery, progress continues. New telescopes are being built. More powerful surveys are mapping the cosmos. Scientists are gathering data with a precision unimaginable only a generation ago. Every observation helps narrow the possibilities. Every measurement brings us closer to the truth. Dark energy may remain mysterious today, but history suggests that mysteries do not remain unsolved forever. The universe has repeatedly surprised humanity, revealing realities far stranger than anyone expected. There is every reason to believe that dark energy will eventually do the same. The next breakthrough may come from a future observatory, a new theoretical insight, or an unexpected discovery hidden within the data. Whatever the answer turns out to be, it will almost certainly transform our understanding of the universe. And that is precisely why the search continues. For all the progress scientists have made in understanding dark energy, the truth is that most of the crucial questions remain unanswered. Astronomers know that the universe is accelerating. They know that dark energy appears to dominate cosmic expansion. They know that it makes up roughly 68% of the universe. Yet they still do not know what dark energy actually is. Solving this mystery requires better observations, more precise measurements, and entirely new generations of scientific instruments. Fortunately, humanity is entering one of the most ambitious eras in the history of astronomy. Powerful new telescopes, both on Earth and in space, are being designed specifically to investigate the nature of dark energy and the future of the cosmos. These observatories will map the universe in unprecedented detail, measuring millions of galaxies across enormous distances and looking farther into cosmic history than ever before. One of the most important missions is the Euclid Space Telescope, developed by the European Space Agency. Euclid is designed to create a three-dimensional map of the universe covering billions of galaxies. By measuring how galaxies are distributed across space and how their light is distorted by gravity, Euclid will help scientists determine how cosmic expansion has changed over time. Its observations may reveal whether dark energy behaves exactly like Einstein's cosmological constant or whether subtle changes occur as the universe evolves. Another major project is the Nancy Grace Roman Space Telescope, often described as one of the successors to the Hubble Space Telescope. Equipped with an enormous field of view and powerful infrared instruments, Roman will observe distant supernovae, study dark matter, and investigate the acceleration of the universe with extraordinary precision. Many cosmologists hope that Roman will provide some of the strongest evidence yet regarding the true nature of dark energy. Meanwhile, ground-based observatories are contributing their own revolutionary datasets. The Vera C. Rubin Observatory, for example, is expected to generate one of the most detailed surveys of the night sky ever created. Its legacy survey of space and time will repeatedly image the sky for years, tracking billions of celestial objects and helping researchers understand how cosmic structures evolve. This vast amount of information will allow astronomers to test competing theories of dark energy more accurately than ever before. Future observations may reveal whether dark energy remains perfectly constant throughout cosmic history. If tiny changes are detected, the implications would be enormous. Such a discovery could indicate that dark energy is not vacuum energy at all but rather a dynamic field evolving with time. This would force physicists to reconsider many of the assumptions underlying modern cosmology. It could even point toward entirely new forms of physics beyond the Standard Model and general relativity. There is also the possibility that future observations may uncover evidence supporting modified theories of gravity. If the acceleration of the universe is caused by changes in gravity rather than dark energy itself, precise measurements of galaxy motion and large-scale structure could reveal those effects. In that case, the solution to the mystery might require rewriting some of our most fundamental theories. Beyond dark energy, future telescopes may answer related questions about dark matter, cosmic inflation, black holes, and the origin of structure in the universe. These mysteries are deeply connected. Understanding one often helps illuminate the others. Many scientists suspect that the ultimate explanation for dark energy may emerge from a broader theory that unifies multiple aspects of cosmology and particle physics. History shows that advances in astronomy often produce discoveries nobody expected. Hubble was built to study galaxies but helped transform cosmology. Observations of supernovae intended to measure deceleration instead revealed acceleration. It is entirely possible that the next great breakthrough regarding dark energy will arrive unexpectedly. A future telescope may detect a phenomenon that forces scientists to rethink the entire problem. This possibility is one of the most exciting aspects of scientific exploration. Every generation builds better instruments, expands humanity's view of the cosmos, and discovers realities previously hidden from view. The search for dark energy continues because the answer has the potential to reshape our understanding of existence itself. Future observatories may finally reveal whether dark energy is a property of space, a new field of nature, evidence for modified gravity, or something even stranger. Whatever the answer turns out to be, the coming decades could become one of the most important periods in the history of cosmology. Humanity may finally learn what is driving the expansion of the universe and what fate awaits the cosmos in the far future. Yet even if future telescopes provide extraordinary new data, one final question remains. Can dark energy ever be fully explained, or will it remain one of the universe's deepest and most enduring mysteries? Dark energy is often described as the greatest mystery in modern cosmology, but perhaps an even deeper question remains: can it ever truly be explained? Throughout history, humanity has repeatedly encountered phenomena that seemed impossible to understand. Lightning was once considered supernatural. The motion of planets appeared mysterious. Even gravity itself puzzled generations of scientists. Yet over time, observation, experimentation, and theory transformed mysteries into knowledge. Many researchers believe dark energy will eventually follow the same path. Others are less certain. The challenge is that dark energy differs from most scientific problems humanity has faced before. We cannot isolate it in a laboratory. We cannot directly observe it with a telescope. We know it exists only through its influence on the expansion of the universe. In many ways, it is like trying to understand an invisible ocean by watching the movement of distant ships. We can measure the effects, but the underlying cause remains hidden. This limitation makes dark energy extraordinarily difficult to study. Nevertheless, science has overcome similar obstacles before. Black holes were once purely theoretical objects inferred only through their gravitational effects. Today, astronomers have photographed the shadow of a black hole and detected gravitational waves produced by black hole mergers. Dark matter remains invisible, yet its distribution can be mapped through gravitational lensing. History suggests that indirect evidence can eventually lead to profound understanding. Some physicists believe the solution to dark energy may emerge from a future theory that unifies general relativity and quantum mechanics. At present, these two pillars of modern physics describe different aspects of reality. General relativity governs gravity and the large-scale universe. Quantum mechanics governs the microscopic world of particles and fields. Both are extraordinarily successful, yet they remain difficult to reconcile. Dark energy may represent a clue pointing toward a deeper framework capable of connecting them. Others believe the answer could involve entirely new particles or fields. Just as the 20th century revealed neutrinos, quarks, and countless other previously unknown components of nature, the future may reveal forms of energy that have not yet been imagined. Dark energy could be the first visible sign of a much larger hidden sector of physics. There are even more radical possibilities. Some theories suggest that our universe may be only one region within a larger multiverse. In such models, dark energy might not require a traditional explanation at all. Instead, its value could vary from universe to universe, with observers naturally finding themselves in regions where conditions permit galaxies and life to exist. This idea remains controversial, but it demonstrates how profoundly dark energy challenges our assumptions about reality. Another possibility is that the mystery itself may transform over time. Future observations could reveal that dark energy is not a single phenomenon but a collection of related effects. What appears today as one problem might eventually be divided into several smaller questions with different answers. Science often progresses in this way. Complex mysteries gradually become more detailed and more precise as knowledge expands. Regardless of the outcome, the search for dark energy has already changed our understanding of the universe. It revealed that most of reality is invisible. It demonstrated that cosmic expansion is accelerating. It forced scientists to confront the possibility that empty space possesses physical properties capable of shaping the fate of the cosmos. Few discoveries have had such profound implications. The answer, whenever it arrives, may reshape physics as dramatically as relativity or quantum mechanics once did. It may reveal hidden aspects of space and time. It may explain why the universe exists in its current form. It may uncover laws of nature far beyond anything humanity currently understands. For now, however, dark energy remains unresolved. We stand in a position similar to astronomers before the discovery of galaxies beyond the Milky Way or physicists before the development of quantum theory. We know enough to recognize the mystery, but not enough to solve it. Yet that is precisely what makes dark energy so fascinating. It reminds us that the universe still contains secrets waiting to be discovered. Every observation, every telescope, and every new theory brings us closer to the answer. Whether that answer arrives next year or centuries from now, one thing is certain: understanding dark energy will transform humanity's view of the cosmos. And as we reach the final chapter of this journey, we will step back and consider the full significance of this extraordinary mystery, a force that appears to dominate the universe while remaining almost completely unknown. As we reach the end of this journey, one remarkable fact remains unchanged: the universe is far stranger than humanity once imagined. For centuries, people looked into the night sky and believed they could see most of what existed. Stars filled the heavens. Galaxies stretched across the cosmos. The visible universe appeared vast beyond comprehension. Yet modern science has revealed a very different reality. Everything we can see, every star, every planet, every galaxy, every black hole, every living creature, represents only a small fraction of existence. The overwhelming majority of the cosmos is hidden. Dark matter shapes the structure of galaxies. Dark energy controls the expansion of the universe itself. Together they dominate reality, yet their true nature remains unknown. Among these mysteries, dark energy stands alone. It is not simply another astronomical puzzle waiting to be solved. It influences the fate of the entire universe. It determines whether galaxies drift apart forever, whether the cosmos freezes into darkness, or whether reality itself faces a more dramatic destiny. Every distant galaxy carries evidence of its existence. Every measurement of cosmic expansion points toward its influence. Yet despite decades of research, scientists still cannot answer the most basic question: what is dark energy? Is it vacuum energy embedded within empty space? Is it a dynamic field evolving across cosmic time? Does it reveal hidden dimensions beyond our perception? Could it indicate that our understanding of gravity is incomplete? Or does the answer lie within a completely new branch of physics that humanity has not yet discovered? At present, nobody knows. That uncertainty is not a weakness of science, it is one of its greatest strengths. Science advances by confronting mysteries rather than avoiding them. Every major breakthrough begins with a question that seems impossible to answer. Dark energy represents one of those questions. It stands at the frontier of human knowledge, waiting for future generations of astronomers, physicists, and explorers to uncover its secrets. Perhaps the answer will come from a powerful new telescope mapping billions of galaxies. Perhaps it will emerge from a revolutionary theory connecting quantum mechanics and gravity. Perhaps it will arrive through a discovery nobody has yet imagined. History suggests that the universe often surprises us. Again and again, reality has proven stranger, larger, and more fascinating than expected. There is every reason to believe dark energy will continue that tradition. What makes this mystery especially profound is that it concerns not only the universe today but also the universe tomorrow. Dark energy is shaping the future at this very moment. Every second, space expands. Every year, galaxies move farther apart. Every billion years, the the structure of the cosmos changes because of this invisible influence. The future of the universe is unfolding now, driven by a force we still do not understand. In a sense, dark energy reminds us how much remains to be discovered. Humanity has walked on the moon, photographed black holes, detected gravitational waves, and explored the deepest reaches of the observable universe. Yet the dominant component of reality remains mysterious. We have learned enough to recognize our ignorance, and that recognition is often the first step toward discovery. Somewhere within the laws of nature, the answer exists. The universe already knows what dark energy is. Our task is to find out. Until then, dark energy remains one of the greatest scientific mysteries ever encountered, a silent force stretching the fabric of space, guiding the evolution of the cosmos, and challenging everything we think we know about reality itself. If you enjoyed this documentary and would like to support more deep space explorations, don't forget to subscribe to the channel. Your support helps bring more long-form documentaries about the universe, black holes, dark matter, cosmic mysteries, and the future of the cosmos. Thank you for watching, and until our next journey into the unknown, keep looking up. The universe still has many secrets left to reveal.